Hello and welcome back to Dr. Logic awkwardly re-records the introduction to one of her videos because she forgot to hit record on the previous take. In this video, I want to introduce to you the notion of some of our substitution instances being allowed and some of them not being. So basically the idea is we want to ensure that whenever we do a substitution instance, we don't end up making an occurrence of a variable that had been free before we did our substitution. Because remember, we can only do substitution into the free variables. We don't want to make that occurrence of the variable end up being bound as a result of substituting in. So basically, this happens when you have a quantifier that is binding some variable. You have another variable that occurs freely, and then you substitute in that variable that's bound in for the one that had been free. The reason we don't want to do this is that it can potentially lead us from a true formula to a false formula. And it will also cause problems with our proof theory when it comes time for us to formally define the semantics of predicate logic and formally define our proof theory. So I believe that that is all I needed to tell you. And now I'm going to stitch this bit of the video back to the bit that actually did record, and hopefully everything will make sense. See you in about 2 seconds.
I think I may have accidentally paused, but I think I've gotten us back up again. So let's keep going. This time, I will hit the thing that brings up my whiteboard, not the thing that pauses my recording. So let's have the definition of allowed substitution. Trying to move the toolbars out of the way. Anyway, definition. This is for the notion of allowed substitution. And basically, a substitution is going to be allowed if it doesn't result in variables that occurred freely in the original formula becoming bound in the resulting formula. So what that means is that in pretty much all cases, it's going to be allowed. But let's say this formally. So if phi is a well-formed formula, tau is a term, x is a variable, then we say that tau can be substituted in for x in formula phi in the following cases. So this is when the substitution is actually allowed. If phi is atomic, then as we've said many times before, all variables occur freely, therefore any substitution will be allowed. So if phi is atomic, then tau can be substituted in for x in phi, and you just do it according to the previous definition. If phi is of the form not psi, well, then tau can be substituted in for x in phi if it can actually be substituted in to psi. So just ignore the sentence, ignore the negation, and look at the remainder of the formula. So if tau can be substituted in for x in formula psi. If phi is of, I don't need to say that. If phi is either psi1 or psi2, psi1 and psi2, or psi1 implies psi2. So again, we'll just kind of make it easier on ourselves so that we don't have to write out all of the cases. This little star will just represent any of conjunction, disjunction, or implication. So if it's one of these, then tau can be substituted in for x in phi if it can be substituted in for x in both psi1 and psi2. So even in the case of a disjunction, you still need to be allowed to do it in both of them, because you never know which is the disjunct that is actually the one that's making the formula true, if it is true. So this leaves just the quantifiers. So if phi is of the form for all y psi, or it's really hard writing both y and psi in the same formula. But anyway, if it is for all y psi or exists y psi, tau can be substituted in for x in phi if either, so there's two possibilities, either x does not occur freely in phi, or case 2, tau can be substituted in for x in psi, and here's the crucial part that prevents us from illicitly binding variables that were not bound before. So if tau can be substituted in for x in psi, and y is not in any of the variables in tau. So if what we are substituting in is something that doesn't involve y and x is free, then this is fine. But if tau contains y, then putting it underneath the scope of a for all y or an exists y quantifier is not going to be allowed. Now, in this other case where x does not occur freely, well, you'll remember from our previous definition, what this means is that you perform your substitution instance, but you just get back what you put in, nothing changes. So it's only really in the second case, so where you have something that can be substituted in, and you check to make sure that no variable ends up getting bound that didn't occur bound in that instance before. So I'm going to give you an example of a substitution instance that is not allowed. So why don't we pick red so that we can see very clearly that this is going to be a bad substitution. A substitution instance that is not allowed. Because the thing with definitions is, yes, you want to be able to understand when you have a case that falls underneath the definition, but often a good way of really understanding what the scope of a definition is to find the cases that don't meet the requirement. So it's just kind of another tool in your arsenal for helping you comprehend and understand the definitions. Definitions are one of the most important parts of the study of logic. So you really want to know how to reason with them when something meets a definition, but also when something doesn't. So here's just an example of that, of a substitution instance that is not allowed. Let phi be the formula, for all y, x doesn't equal y. Then the substituting of y in for x is not allowed. Now, this formula here could potentially be true. The reason why substituting y in for x is not allowed is because the resulting formula is something that's going to be necessarily false. And we'll come back to this example once we start talking about the semantics of predicate logic, just so that you can see for yourself. So why is it not allowed? First of all, let's check our conditions here. It is, so phi is of the form for all y psi for some psi, so tick. X is in the set of free variables of phi because there's no quantifier binding it. But the problem is that y is in the set of variables in psi. So the result would actually be for all y doesn't equal y. And this is actually going to violate one of the fundamental axioms of identity, which just says that everything is identical to itself. That's saying something different from every y is not identical to an x. So taking this x, changing it to a y, brings it under the scope of that quantifier and changes what the sentence is saying. And that is why it's not going to be allowed. So there you have it. Whew, we have reached the end of what we need in terms of basic definitions for substitution. We'll come back to these definitions as we start looking at truth conditions, as we start developing rules of proof, so that you can see why we had to go through all of them. They're all covering kind of various cases that ensure that we end up with semantics and proof theory that are both sound and eventually, though it's going to be a long time and many more videos before we get to that, complete. Since we've covered all of this, talking about kind of the basic machinery of predicate logic, kind of the next thing that we need to do is just talk about, like, what can you say in it? So what can you say both in terms of representing things in the English language, but also if I give you a bunch of symbols, how do you get from them back into something that is English? So this goes back to the idea that logic is fundamentally learning a new language. And one of the most important qualities or properties of a language is intertranslatability. Can you go from language 1 to language 2, and can you go back? That will be the topic of our next series of videos. So join me then for fun with predicate logic. Take care. See you then. Cheers.